Ooh, it's really bad. Oh, there we go. There are substitution reactions, and we've learned about one of these so far. It was the radical halogenation reaction, but the one that we're interested in are nucleophilic substitution reactions. Okay? We learned about radical halogenation reaction. That was a substitution reaction, but now we're going to learn about nucleophilic substitution reactions, and the most important one that we're going to learn about is called the SN2 reaction. And it simply means a substitution reaction. It's nucleophilic or involves a nucleophile. And the two part is related to kinetics. And we're not going to do any kinetic calculations, but the two will become self-evident when we actually get to it. And the typical substrates we're going to use for these, we've been working with. We're going to draw a chiral molecule. It's a very simple type of prototypical substrate that we work with. We're going to be working with alkyl halides, like this one. The one that I have here has a chiral center drawn. And it's not the end of the world that my handwriting isn't the best. You simply just have to transcribe this into your own notes. This particular molecule we can look at. We know it's a very simple molecule. We know we would call it 2-bromobutane. And further, we would be able to calculate that this is S2-bromobutane, and you should be able to confirm that on your own with your knowledge of chirality and assigning RS stereochemistry. Further, this particular molecule, we actually know how to make from simpler molecules. We could make this particular molecule from radical halogenation. Right? If we took butane and bromine and did radical monohalogenation reaction, we would get this as one product. The other way we could do this that maybe might be a little bit better is we could do electrophilic addition, perhaps to alkene, like this molecule, right? What reagent would we add to this molecule to make this particular molecule? Well, if we added HBr to this alkene, right away we would make this as the major product, since the carbocation, if we add HBr in these reactions, is favored here. So, like I said, we already know a lot about these molecules, how to name them. We know chirality. Naming is quite simple. And we also know at least two methods. We might even know a third method that I'm not going to mention right now, but we know at least two methods to make this type of molecule. The key feature about SN2 reactions now is that we're going to react this with a species that we're going to call a nucleophile, and in time we'll learn how to identify substrate and nucleophile, just like we had some issues with acid and base. We'll find out it's quite simple for us to identify substrate and nucleophile, but the substrate almost always is the carbon-containing bit. The nucleophile is almost always the bit with lots of pairs of electrons, usually with a negative charge, and the substrate is also attached to a highly electronegative atom, which will become what's called our leaving group. And this particular reaction was so interesting is because when these species were reacted together, a substitution reaction took place. People knew that, but what was particularly interesting about this is that the stereochemical consequences of this reaction were fairly stark and unmistakable. What I mean by that is when this reaction was done, the newly formed stereocenter has exactly opposite stereochemistry, 100%. If this is S, then this inverts, and in this example, if we recalculate it, it becomes R, and this particular molecule, if we were going to name it, would be R2-butanethiol. If this was an alcohol, it would be butanol, and sulfur equivalent of an alcohol, if we replace the O with sulfur, it becomes thiol as the functional group name. So we don't need to worry too much about this, but thiols are this particular class of compound. They're particularly smelly. They have a horrible odor. It's the smell in natural gas is based on thiols, and skunks also use thiols to defend themselves against other things, right? So thiols are important compounds in nature. They're prevalent all over biology, biochemistry, and thiol is a name. You'll hear it again if you do any more work in life science or physical science. We'll talk now about the mechanism of this reaction in detail. And along with it, we're going to simultaneously discuss stereochemistry. So we're going to discuss the mechanism and stereochemistry. They go hand in hand with one another. We'll start out by drawing a nucleophile. We're going to put 2 electrons up next to it right here. Usually it'll be negative charge, so sure, we can put a negative charge there. And we'll draw in kind of a generic substrate here. I'm just going to draw 1, 2, 3. It's just arbitrary groups, so we see where they go. And we're going to draw on this particular molecule an electronegative atom. We'll represent that by being delta minus, delta plus. This bond is polarized in this direction. So X, whatever it is usually going to be an electronegative atom. And in chemistry, X is an unknown, but usually it means chlorine, bromine, iodine, or fluorine. Usually, but not always. So just usually means an electronegative atom. Nucleophile, again, it's going to be some species with usually negative charge on it, but will always have a pair of electrons available. And another key feature about this particular carbon is it's going to have to be sp3 hybridized. Okay? That carbon's going to be sp3 hybridized. The mechanism we're going to draw very carefully in black here, right? And it's very, very simple. It happens in a collinear fashion where the nucleophile attacks carbon specifically at this little location here. That's at the back side of carbon in terms of looking down this particular carbon X bond. We attack basically on the 180 degrees away from this particular bond on the other side of the molecule. It can only attack this way. Front side attack we saw in our pre-lecture video would be something over here, or sideways attack, or something else. Doesn't happen. The only way that this reaction happens is by nucleophile approaching carbon at this particular location. When this happens, a bond starts forming, and simultaneously, the carbon X bond breaks. So this is it for the mechanism. For SN2 reaction, it's always this, just these 2 arrows. And these 2 arrows, as you already know, mean that this bond is breaking. This is why it becomes our so-called leaving group. And this bond is forming. So you can already predict what the product should look like. The only key feature now is that we have to be aware that the stereochemistry, so-called, inverts. And this right here, how I've drawn this, would be an inversion of stereochemistry. We can see that the stereochemistry has inverted. These 3 groups are kind of going this way. Now they're going to the right. And if we were to calculate R or S for this, if we were to assign some priority numbers to these things, we would see that it had flipped here. So the important details are this mechanism, and that if we have a chiral center here, that the stereochemistry inverts. Okay, we'll move on a little bit. We're going to look at this just the same exact slide we had moments ago. And we're going to look at this from a slightly different perspective. We're going to draw a nucleophile. This time we're going to draw the nucleophile with 2 electrons in some orbital. We're going to draw our carbon like this. We're going to have X atom here, and we're going to draw some orbitals here this time. I'll explain what these orbitals are momentarily. But there's an sp3 orbital from carbon. That's this unsymmetric one that has a small lobe here and a large lobe here. For this particular bond, we're going to use X. It could be chlorine or fluorine, and so we'll use a p orbital. And this bond in the middle is a sigma bond, and there's 2 electrons in it. So we're drawing this kind of in a funny fashion, but nucleophile just has some electrons. We're going to draw them in an orbital. Carbon is sp3 hybridized. The bond that makes a sigma bond between carbon and the X group comes from an sp3 orbital. In this case, I'm just using a p orbital for our X group, and there's 2 electrons in that bond. And what happens is these 2 electrons approach this particular direction. And The second thing that's going to happen is this bond is going to break, but there's a very, very brief transition or transition state that happens. And we draw a transition state in a bracket like this, a very, very reactive intermediate, something that we could never isolate. And for a very, very brief moment in time, this carbon atom becomes something that looks like sp2 hybridization with a p orbital that is simultaneously has some bonding characteristics with the X group and some bonding characteristics with the nucleophile. So this starts approaching. This bond starts forming. These groups that are attached to carbon start getting pushed. These groups are getting pushed this way. They're moving out of the way of these incoming electrons. So they get pushed halfway until they're kind of in a plane right here. Hybridization on carbon changes. And carbon obviously can't be bonded to 5 things, but this is what we think at some point between the start and the end of this reaction, the transition state looks like. And this also helps explain if this process keeps going, if the nucleophile keeps going this direction, then the bond will get stronger here, the bond will get weaker here, and these groups will continue to push until we get back to sp3 hybridization for carbon. These pictures aren't perfect, it's not really the point, but we get back to sp3 hybridization, and we have a newly formed sigma bond here, and our X group is left with 2 electrons, they'll be negatively charged, and it's this transition state here that helps us understand why 100% of the time the stereochemistry inverts. When we had carbocations, our incoming nucleophile would come in from the top of a p orbital and the bottom of a p orbital, 50-50. But here, there's no chance for different enantiomers to form. Only one can form if we have a chiral center. And it's the result of this transition state where everything is attached for a brief moment. And then as this bond finally forms, this bond pops and leaves. And so this kind of diagram here in our notes should give you the feeling and understanding why the stereochemistry inverts. If you wanted, you could just number these groups 1, 2, 3, 1, 2, 3, and just 1, 2, 3, and you would see they kind of flip almost like an umbrella in the wind. And so that helps us. This particular transition state diagram, if we were going to draw this energetically, it's quite simple to do. We have energy on this axis. We have our reaction coordinate or reaction progress on the x-axis. At the starting point, some energy. We have our substrate attached to a leaving group, and we have a nucleophile. These are going to go through some high energy transition state up here with some associated activation energy. And up at the top of this transition state, the nucleophile will temporarily be bonded to carbon and the leaving group. And we'll have these 3 groups attached to our carbon here. Hybridization changes. And then for this reaction to actually work, it'll have to be exothermic. And our final product will have the nucleophile attached. And we'll have some leaving group that's left. Okay. Oh, let's make one little note here that our nucleophile is negatively charged. We're adding it to a substrate. Maybe this is a little bit hard to read, a little bit small today, but this particular diagram is not the most important thing we're going to do today. But just energetically, this is a refresher of what's happening in this reaction. It's quite simple. There's only one transition state where all species are connected. Starting reagents are usually higher in energy than products. That's what makes a reaction favorable. And basically, we start with the leaving group attached. The leaving group leaves. The nucleophile is not attached, but it attaches in the middle. And then finally, at the end, is attached in our final product. We're going to put some 4 or 5 points right on paper to summarize kind of the ideas and concepts we're working with, codify them in paper by writing them down.